Okay, so you found the video for today's lecture. This lecture, this video should cover right about here in what I have as on a timeline here. This is Monday's lecture, and since you're watching it, I assume you know that we aren't meeting in class. Monday, I suppose, 10:14, but whenever you're watching it, right, there's some convenience added here. So in this video, I'll go over an example from the material that we covered last Friday, introducing covariance and correlation. I'll also introduce a topic that was originally scheduled for Wednesday, but it's nice for this format in that it's, it's a bit of a result of using the expected value operator that's in Chapter 4, but maybe isn't such an important concept as the linear combinations of random variables that we will talk about on Wednesday. Now here's kind of the timeline down here. Homework 7, if you're watching this on Monday, was then already due, and that is it will be on exam 2, which is coming on Friday. When we meet again on Wednesday, we will have quiz 7, and we'll still make that a partner quiz as planned. Okay, that's on Wednesday. We'll still have the exam on Friday. What's changed there is it covers less material due to this missed lecture and had the rearrangement this week. I do have it covering, so Chapter 3, okay, I have this where is it, 3B and 4B. What I mean is this is our second go-around in Chapter 3 and Chapter 4. So all of Chapter 3 is on the exam, both of our forays into Chapter 3. That was introducing distributions the first time around, and then joint distributions the second time around. And then Chapter 4, we we were introduced the first time with just the expected value. We then use the expected value to talk about how to find the mean of a random variable and a variance of the random variable. And then we've now talked about how to use that on joint distributions to have the covariance and correlation. Okay, and so that'll be what the exam is on. What won't be on the exam, which was originally planned to be on the exam, is Chebyshev's theorem and linear combination of random variables. Okay, that will now be saved for a later exam, and that's part of homework 8, and also then quiz 8. So homework 8 is now due after the exam on Sunday, and quiz 8 will come on the Monday after the exam. Okay, so let's get into this example using covariances and correlation. Now, to do this, I have if we ever need it, the exam 2 formula sheet. Now, this formula sheet also still includes, I'm not going to change it, even though this stuff won't be on it, right? That's basically what we mean. But we will be referring in this example to kind of this stuff right here, okay? So if we ever need it, we can pull over those formulas, okay? So let's get into it. So this example, actually, I'm going to be relying on a previous example as well here. So there'll be actually 2 examples, but I got to define this new example. We'll let X and Y denote the fish population in or at maybe 2 regions. Maybe these are 2 regions of Lake Michigan, okay? Could be any lake, but let's actually call it Lake Michigan so keep it kind of local, with the given joint PDF as follows. Given joint probability density function, okay? So f of xy is known to be x1 plus 3y squared over 4 in the region of x between 0 and 2 and y between 0 and 1, otherwise, 0 elsewhere. Now you might ask, well, if x is the fish population, what do you mean between 0 and 2? 0 and 2 fish? So let's say, no, that's not what we mean. So these units are in, so the fish population in Lake Michigan is like 25 million total fish. So 25 million. So at these 2 places, maybe you have keeping track of how many fish are going through a gate, or using fisherman data to do this, right? So maybe what we have here is the fishing population is controlled to ensure that x is less than 2 and y is less than 2, where these are, the units here are 100,000 fish. So that's for both of these. So that's kind of a lot, right? So we're talking between 0 and 200,000 fish. So naturally, by the nature of fish, it's a discrete distribution, right? You can only have integer numbers of fish. So in its nature, x and y are discrete, but what we are imposing a continuous model because we have such huge numbers, right? So this number is so big that we're modeling this as continuous. So discrete in nature, but modeling using continuous random variables. Okay? Right, and so let's make this even more of a example that we can put our, have some intuition for. So let's say x is like, which one's going to be more? Let's say x is Chicago, so there's some like port out in Chicago, and y then, so this is x, the location is, and then maybe this is Green Bay, somewhere else on Lake Michigan. Okay, and what we want to do in this analysis say is like, and so there's a random nature here to this fish population, right? There's sometimes when we go and measure how many fish there are in this near Chicago region, it's 200,000. Other times it's closer to 0, right? And maybe this is just a model. I haven't even looked at like what the surface looks like here, but the chances, or the probability density of x equaling 0 is 0, because x, when you plug in x equals 0 is 0. So we have a low probability of having no fish in that region. However, when y is 0, there is a chance of that, right? If you plug in y equals 0 to the probability density, you're still going to have a non-zero probability, or it'll still be a function of x. These are just some observations of our model. Let's just accept that it's a model, and then let's, move on from there, okay? So we're modeling this as a continuous distribution. Let's first start by what are the typical values, what are the mean values for numbers of fish we see in these two regions, okay? So we're going to start with the expected values of the random variables, so these are the means. So mu of x, that's the expected value of x. Well, this is a joint probability density, so if I go over to our formulas, okay, we look, well, there's the expected value of a function of both x and y. We just want that function, g of x, y here, to be x itself. All right, so what that says is integrate over all of the, both domains, x and y, where you just plug in g of x. Well, g of x and y, I should say, right? But that function we're looking for this expected value is just x. Okay, so we have double integral of x, that's our function of x and y, multiplied by the probability density function, that is a joint probability density function. I'll make my inner integral x, so that goes from 0 to 2, and my outer integral y, that goes from 0 to 1. Okay, let's now just take the inner integral, and let's just evaluate that, right? Let's separate their variables. So we're going to pull everything out of here that isn't x, or doesn't depend on x. That'll go in the y integral on the outside. So we can pull out 1 plus 3y squared over 4. Okay, but on the inside, and I'm going to actually make this red color, what we have left on the inside is the integral from 0 to 2, and there's just an x squared dx. Okay, and then on the outside we still have a dy. Okay, so this integral in here is going to be x cubed over 3 from 0 to 2. Still left over on the outside is dy, the integral 0 to 1, 1 plus 3y squared over 4. waiting to be integrated there and once we get our final result from the middle integral. And well, that just turns out to be 8, 2 cubed is 8, 8 cubes, 8 thirds, and then the lower bound gives us nothing, right? So this just equals 8 thirds. And so then we can take the 8 in the numerator here, divide out the 4 that's in the denominator and the outer integral, and we have a 2 thirds that we can pull out. And then we just have an integral 1 plus 3 y squared dy from 0 to 1 is our bounds. And let's see, this is going to be 2 thirds y plus y cubed, as the 3 is canceled by the 1 third, bounds 0 to 1. And, right, well, that's just 1. Let's do this in a different color. This is now just 1 plus 1, which equals 2. Simplest thing in math, right? So this will just be 4 thirds. Okay, so what does that say? That says that a typical population is 4 thirds 100,000, right? Or 133, right? So typical fish population at Chicago is 133,000. Okay? At wherever we're measuring it. Remember, the units here are hundreds, thousands of fish. And we could do similarly for y. I'm not going to run through it. Similarly, good practice if you want to give it a go. The mean of y is 5/8. All right, so see if you can get to that result, right? That'll be good practice. And so what this means, right, is that a typical fish population at Green Bay is, what's 5/8? What's that, 625? So 62, is that right? I'm going to do a quick check, make sure I get my numbers right. It's really hard to do it when you know that you're being recorded. So 5 divided by 8, yes, 625. So we multiply, so it's 0.625, multiply that by 100,000, and yes, we get 62,500. Okay, so that's what that means. That's like a typical quantity, or it's the things if you made measurements time after time, year after year, however you want to say it, and you kept making those measurements, you would find, and average those measurements, you would find these two numbers, right? That's what our expected value means. Now, okay, what else can we say from this, right? We could calculate our marginal distributions, although we've done that along the way. Okay, let's just do one of them. We can get our marginal distributions. That's not going to help us tell whether, I never even mentioned, like, maybe what we want to know here is, does it when the Chicago fish population is high, does that also mean the Green Bay fish population is high, right? How correlated are these two quantities? So the marginal distribution might help us further, later on, but let's just calculate one. So what I'm referring to now is actually not from this new material, but it's actually from the material previously. I want to calculate this quantity right there, right? So integrate over all possible y values to get the marginal distribution for x. Okay, so g of x is then, what are all y values? Y is only defined from 0 to 1 in units of 100,000, right? X, 1 plus 3y squared over 4 dy, we're integrating over all y. Okay, so that means we can pull out the x over 4. That doesn't depend on y, and we have that integral of the inside, which is just that y plus y cubed that we've already done, right? Now this is starting to look really familiar, right? It's like this outer integral that we did before. Okay, well, again, this is just 1 plus 1 equals 2 on the inside here. 1 plus 1 equals 2, and we just get x over 2. Okay, now that's helpful, right? It's a good thing to know. Right now, this is basically our PDF for just the Chicago fish population all by itself, right? This is defined for 0x to 2, right? Those are the bounds. And another way to calculate, or that we have to calculate our average values then, is going back to, now we just have like a single random variable, is to just take, to get the average, the mean value, is to take the expected value, just the random variable integrated, weighted by its own PDF. Well, the marginal distributions are PDFs of individual random variables, right? So we should be able to check our work from above. So let's go check. Mu of x should then equal integrate over all x times its PDF, which is g of x. Okay, so this is just the integral from 0 to 2 of x times x over 2 dx. So that's x squared over 2. That's then x to the cube over 6 from 0 to 2. And we get 8/6, which is 4/3. And that number should match right there, right? Okay, so along the way we could, if we already have the marginal distributions, it helps simplify that mean value check, right? And you could do the same thing for h of y, and I have this in my notes. H of y, if you do this out, you should get 1/2 1 plus 3y squared. Go ahead, practice that, and then calculate, do the check. Is mu y also 5/8, right? By doing a very similar thing. Okay? Now, let's get back to the question at hand, which is like, okay, so are these things correlated with one another? Do they depend on one another? Like if you know information that the fish population is above the average in Chicago, so above 133,000 at one particular time, does that tell you information that Green Bay's fish population is also going to be higher? Maybe it'll be lower, right? All the fish have now come down to Chicago. Oops, wrong one. Let's see, right? The way we do that is calculate the, to calculate the covariance, right? So let's calculate the covariance, right? In order to get that, go to our equations maybe, or what we derived on Friday, right? Now we're at this one, the covariance. The way we calculate it, right? In fact, that's the better definition, and we use that to kind of get a feel for what the covariance was, right? When one random variable is above its mean, is that more associated with the other random variable being above its mean for positive correlation or positive covariance, or if they have this reverse where one is high, the other is low, and vice versa, that would be the negative covariance, and we talked about that, right? But this is the better way to calculate it. Makes it, to actually do the calculation will be easier. So what we have to do is that expected value of x times y. Let's calculate that. One here, the covariance, the way we're going to calculate it is, one more back, is the expected value of xy product minus the expected value of x times the expected value of y, which we've already calculated, right? So the expected value of x times y is the integral 0 to 1, 0 to 2. That means I've got dy on the outside, dx on the inner integral. But now that function, gx or whatever, so let's see here. This we'll put in red. This we'll put in red, right? This tells you, or that's where the function of x and y goes in that operator, right? Everything else is fixed, that this is the operator of the expected value. So now this is our joint PDF. 1 plus 3y squared over 4 dx dy. Make sure we're matching the x bounds as the inner integral, and the outer integral is the y bounds. Okay? This is a nice integral to take, right? Let's try to separate these into actually two separate ones, right? We should be, sometimes we can completely separate the two variables. So all of the y's go out here. There's a y, 1 plus 3y squared, okay, dy. And we can pull all the x's over here, right? This is just x squared. Pull all the x's there, and then we'll just keep the 4 over on that one. And we can calculate these two separately, okay? This one we've already calculated, I believe. So let's see. Look for this integral here. This integral right there, right? That's y plus 3y cubed in the integrand from 0 to 1. That's right here. Y plus 3y. Oh wait, did we calculate that? Y plus 3y cubed. I don't know, maybe we didn't. I have it in my notes that we calculated this before. It's not a long integral, let's just do it, right? So this one is now going to be the integral from 0 to 1, y plus 3y cubed. If you find it in your notes, then feel free to just refer back to that. Y squared over 2 plus y to the, no, sorry, this is y to the 4th 3/4. Okay? You know what I think it was? I think you calculated along the way to get to the this one right here, somewhere inside here. You probably calculate it. Okay, but let's finish this off. 0 to 1, so you get a half plus 3/4. So that is 2/4 plus 3/4, so 5/4, 5/4. Okay. This other term, it's the other part of the double integral, but we were able to completely separate them here, right? That's just going to be x cubed over 12 from 0 to 2. So you get 8 when you plug in 2 cubed, 8/12 or 2/3. Okay, so all together we get 5/4 times 2/3, which is the 2 cancels there, which is 5/6. Okay, that's only a partial result because that is just the expected value of x times y. So our covariance then, sigma xy, is then 5/6, that's the expected value of xy, minus the mean of x times the mean of y, which we calculated earlier. Okay, so this is mu x times mu y. This is the expected value of xy. All right, do all this out, right? Calculate this. That's 5/6. Quick check over here. The 4 and the 8, the 4 over makes a half. So you got 5/6 there as well. So we get 0. Big, all that work, and you get 0. Okay? So this is a required result if independent. Right? So this should tell us that these are independent. So could we have determined that earlier? I think so, but let's first write this. Required result if independent, and only goes this way, remember. Okay? Finding zero covariance doesn't really require independence, but if independent, then this is a required result. So can we show independence, right? If we come back up here and let's look. If h of y, I'm focusing on back, work that I kind of hand waved over. Here's hy, and here is g of x. Okay. We make a quick note here that to get f of x, y back, we just need to multiply g of x times h of y. So that is just, we show this for all x, y, but this means that these are independent random variables. And from that, right, even at that point, we could have stopped and said, that means that you can give me any information you want about the fish population of Chicago. I won't know anything more about the likelihood of the fish population in Green Bay. That's what the model is telling us. These are independent. They're so far separated across Lake Michigan that their fish populations don't affect one another, right? Okay. And so just a quick check. F of xy, go back to the definition here, was x over 4, 1 plus 3y squared. G of x was x over 2, but the other 1/2, remember it was x over 4, 1 plus 3y squared. We got a half in the h of y term, right? The marginal distribution for y. So multiply those two together, you get f of xy back. Okay, so now this isn't that interesting. like if we now go and take, okay, well now we got the covariance to be 0, what's the correlation coefficient? Oh, hold on. I meant lasso. Um, the correlation coefficient is trivially 0 as well, and that's always the case whenever you've got a 0 covariance. Your correlation coefficient is the covariance divided by the two standard deviations. So whenever covariance is 0, the correlation coefficient is 0. So that is maybe a stronger statement. This just tells us that we have no correlation in our model between the 2 points. Maybe that's what we want. Maybe that's what we observe, and we want no correlation. So that means that the locations are probably very far apart, or something like that, right? And so Green Bay to Chicago, is it enough? Is that a valid assumption of our model, right? So instead, I want to use, finish off this example by referring to a different example. Recall the museum example. We called it the museum example when we went to the slides and looked at the visuals, but this was defined this way. F of xy was x plus y over 3 from 0 to 2 in x, and also, so the bounds here are the exact same. Okay, and then 0 elsewhere. So first we just defined a joint probability distribution like this, did a bunch of calculations, and then we came back and looked at the visuals of this, okay? Let's work through the same thing here. Actually, what I'll do is I'll just set up the integrals and then assume that the calculation can be done, right? So the mean of x is going to be integral over all y, integral over all x, x times the PDF, dx dy. You do that integral, you should get 11/9, right? Check that. Do the same thing in y, the integral over all y, integral over all x, but y, x plus y over 3 dx dy, and you get 5/9. Okay? The other quantity we need to get covariance for this joint distribution, or these two random variables, x and y, is the expected value of x times y, integrate over all y, integrate over all x. Now our function is x times y that we're taking the expected value of. Joint probability distribution in there, dx dy, and you should get 2/3 after that integral. Okay? So from those three quantities, and hand waving our way through the integration process, we have sigma xy equals 2/3, that's the expected value of xy, minus the product of the two means, which is 11/9 and 5/9, and we get something non-zero. I think we get, well, here, I'll just put it over here, -1 over 81. -1/81. Now that's not, well, it looks like a small number. What am I doing? Okay, 1/81, right? But and what this means by the negative, so let's just make some observations for this number here. Okay, having negative covariance, that means that, remember how we defined these two random variables? It was x was time spent in hours in the museum exhibit, so time in hours spent, and then y was knowledge gained from like a exit quiz or exit survey. And what that negative covariance tells us is that the more time spent, right, less learned, right? When you get above the average of time spent, there's a correlation, or there's a tendency to then have learned less, to be less than the mean for the other random variable, which is y. Okay, but this actually doesn't tell us how strong the number 1/81, how strong requires us to calculate the correlation coefficient. Requires correlation coefficient. Okay, so that's what we do next. And so here, the correlation coefficient is, remember, xy over sigma x times sigma y. This is actually capitals. Okay, and so there's actually a lot of work still left to be done here. Okay, we actually need to still calculate the two bottom things, right? We have this number, that one's done, but to get to the two standard deviations, we first need to calculate the variances. Okay, so variances. Sigma x squared, that's the variance of just x, right? That now is the covariance of x with itself. Okay, that's the notation we use. All right, so it's the same. What I mean by that is we're going to do the exact same operation. It allows us to take the expected value. Okay, and so this calculation looks like this. We integrate over all y, integrate over all x. We take x squared, x plus y over 3 dx dy. But we then need to subtract off its mean, right? So the variance of x, remember, is, I'll do this in red, is the expected value of x squared minus the mean of x squared. So that's this term, and now we need to subtract off the mean of x squared, which is 11/9 squared. Okay, so some calculations needed there. That is 23/81. Do a similar thing for y. That's the covariance of y and y. That's the variance, right? So the covariance operator allows us to get the variances if we do the covariance with a random variable with itself. 0 to 1, 0 to 2. Now we plug in y squared, x plus y over 3. There's your PDF. Dx dy. Subtract off the mean of y squared, that was 5/9, and we get 13/162. Okay, ugly numbers, right? Go to the decimal values if you want. But in the end, right, now we can come back and actually calculate our correlation coefficient to get a measure of how strong this negative covariance is, or the negative relationship is. The correlation coefficient is then -1/81. That's your covariance. Standard deviation with x is the square root of the x variance. Square root of the y variance goes here. And we get minus 0.51 or 418. And that's actually moderate. Okay, remember, correlation coefficient is bounded between 1 and -1. And the closer you are to 1 or -1, the stronger the correlation. So that stronger there is a dependency on, when one is high, the other's low, or when one's way above its mean, the other one's way below its mean. So, yeah, we interpret this as a moderately negative correlation. Okay? All right, so there's, obviously a lot of calculations required to get to a correlation coefficient given a joint probability distribution. If we ever get to a case where you get zero covariance, right? Probably built into the model that there is, so that was this one right here, probably built into the model that they're independent and there's going to be no correlation. But, right, if there is a non-zero covariance, you need to, along the way we calculated the mean, we calculated the other mean, we calculated the expected value of x times y, then we were able to get to the covariance, but then we needed to calculate the variance of both variables, take their square roots to get to their standard deviations. I mean, you basically calculate every single quantity we've ever talked about, all to get to the correlation coefficient. But once you're there, this number now means a lot, right? That tells us that not only is they negatively correlated, so, all right, that would mean that x was here, y is here, and a negative correlation would mean, you got some observations, most of the observations maybe are here-ish, but they would have this tendency, right? But not so tightly tied together that's not like in a single line, but there's some noise about this. But the general tendency is that the more time you spend, the less you learned, right? Which is maybe a bad model or a bad museum exhibit or something, right? Maybe you want to change your methods or change the way you're modeling your museum exhibit. Okay, so that's the end of this example on using covariances and correlation coefficients. All right, so for the last bit here, we'll talk about Chebyshev's theorem, which again is something that's actually a pretty powerful statement. It has a pretty easy form. And why? So we'll write down the form here in a second, but why it's so powerful is I've written down in English language basically what the theorem is. We may hand wave our way through the proof, maybe actually write it all the way out since this is a video and you're free to watch any parts of it that you want. But why it's powerful is this word here, arbitrary, maybe this word here, unknown. So oftentimes in using probability theory, in statistics in general, we often want to we often have to assume something about a population and its nature. What we mean is we say when we model a system with a mathematical model, right? Model a random variable given a particular mathematical form. We don't actually know whether it's true or not, so this theorem applies whether or not we've got the right form, right? So what it says is that a random variable x has a probability of taking on a particular value. Well, not a particular value, can take on any value within k standard deviations. Now, there is a, in order to make a statement that's accurate here, we need to know the standard deviation or be confident in it of its mean. And so there's that mu, okay? And that is at least 1 minus 1k squared. So it's not a, you're not going to get a probability out of this, but you're going to get a lower bound for a probability. So let's write this down in our mathematical language. What we mean here is the probability that x falls between, well, is in a window near its mean. How far away can we go from the mean? K standard deviations. So we go k minus k sigma, k plus sigma. Okay, so we are in that range between k standard deviations to the left, k standard deviations to the right. That is at least, so it's a upper bound, 1 minus 1 over how many ever, standard deviations away we went out. Okay, so this is it written out in our mathematical language. So this inequality means a lower bound, not an actual probability and not an exact probability. And it's just helpful in reality, right? When you are confident, so let's write this, helpful when confident about the mean and standard deviation, but don't know or aren't confident in assuming a distribution all the way. Okay, but unknown distribution f of x. Okay, and the reason it falls in here is that really the proof requires or is heavily reliant on the expected value operator. And I'm actively considering here whether we go for it or not. I might just leave it out. I don't want to make this video too long, but yeah, let's just jump into the examples of using it. And I'm happy to, I might just pull my notes up at the end and just, say, here's the proof, and I can walk through it that way. That's what I'll do. Okay, so let's just jump into the examples of it. By the way, if this wasn't a video, we wouldn't be showing the proof like during class time. So this would be a supplementary video anyways to show the proof. Okay, so let's look at an example of applying this. Let's say we have a random variable x that has, or we're confident that the mean of x is 8 and the variance in x is 9, but we have an unknown f of x. So I'm going to draw a picture, but by definition of the example, this thing is actually unknown. So if I draw a picture of the distribution, I'm just showing you one possible distribution that it could be. Okay, so this is x, this is f of x, and let's say Well, we know it has to be mean is 8. So let's make this thing kind of right skewed. Let's put 8 there, 4 there. Now I'm being careful here because the standard deviation then should be about 3. So if I go 3 away, we should have, most of the distribution here. So sigma x, the standard deviation is 3. So that brings us down to, so let's make the peak somewhere here, and no, somewhere like here-ish, and most of it then. So what I'm doing is here is that I know the mean needs to be at 8. Sorry, I'm just trying to figure out what a good shape to this will be that matches these two numbers with the mean here, and yeah, this looks pretty good. We'll have it more sharply skewed there. Something like that. Maybe we could even be more aggressive. How about over here we have it have like a little bump or something, okay? Let's just give it some shape. I don't know. It doesn't matter too much. So then this would be like 12. I think the standard deviation of what I've actually drawn is way too big, but you get the idea. Okay, so let's do some calculations with Chebyshevs out of this. So this is my assumed form for the distribution, and we're just going to use this for visuals, but the Chebyshevs can be used just in general, and it's always this like upper bound or lower bound depending on the questions you're asking. So let's what if I want to know what's the probability I'm somewhere between 4 and 20? So 20 is going to be, so that's 12. I'm jumping by 4s. There is 16. No, not 4, negative 4. Okay, so then that would be negative 4. There's 0, 16, and 20. Okay, I'm going to have to be really careful with my picture there, okay? So now let's see. What's the probability here? Okay, the probability between negative 4, x is between negative 4 and 20. Well, if I just look at this number, to go from the mean 8 to get up to 20, well, that's 12 more, right? So this 20 here is 12 higher than the mean. That is the mean plus 12, so that's 4 standard deviations. And also on the back end, we've now gone 4 standard deviations the other direction. So this is mu minus 4 sigma. Okay, so now that I've, really all of this was just to get at this number here, 4. I've gone up and down 4 standard deviations, so I can just apply Chebyshev's theorem directly. This has a must be at least 1 minus 1 over 4 squared, which is 1 over 1/16, or sorry, 1 minus 1 over 1/16, so that's 15/16. So what that is saying is that as we've drawn the picture, this area, remember the total area under the curve is 1 and always 1. This area is at least 15/16, if not bigger. Okay, and in fact, with the way I've drawn it, it's probably much bigger. I have very little tails left over here. All right, and this is all governed by what the standard deviation is, and that's why I was trying to be so careful to draw a picture that was actually accurate. Remember, this 8 is the mean, okay? And k we determined was 4 by the question being posed about this problem, right? Let's see if we can do something else. Okay, so that was one thing. Let's do another one. What if we said, what is the probability that x minus 8 absolute value is greater than or equal to 6? Now that looks a lot different than what we had before, right? But what we are subtracting off from x here is 8, which is the mean. That's not an accident, right? So what we're saying is that what's the probability that I'm more than 6 away from the mean? Okay, so if I'm going to reuse the same image, I can definitely do it here, but choose a different color. So here's my mean, 8. And all I'm saying is in either direction, what's the probability I'm more than 6 away? Well, 6 away puts me up at like 14, which is there. And 6 to the back is like 2. So now what I want to know is, what's the probability I'm out in these tails? Okay, well, Chebyshev's theorem only makes a statement about the center. Okay, so in red, what we had before, and I've covered over it with the green here, but before in red, I was making a statement about the center. So Chebyshev's theorem gives us a lower probability bound. Lower probability bound. Okay, when we ask a question about the center. When I come to green now, the second question, now we are out in what we call the tails of the distribution, right? The extreme ends. And so Chebyshev's theorem gives us an upper probability bound because it'll actually give us a lower probability bound for what's in the center, right? This bit here. Okay, so we can relate this question over here to something that we can actually calculate with Chebyshev and show that it's an upper probability bound, right? This is actually 1 minus the probability. I'm probably going to run out of space here, so I'm going to shift it over. 1 minus the probability of mu minus 2 sigma x mu plus 2 sigma. That what we're saying here is this, well, we can just keep using green. Oh, hold on. Green, this right here, yeah, I should do this better. This range right there is that bit there in the center, right? So if the whole area is 1, the two added together, this is the outer, these are the tails on the that we're trying to ask the question about, right? Tails, and then this is the center, right? Okay, we'll just zoom out. So now we can lower bound this term I have here, and it's because we're doing 1 minus it actually acts as an upper bound, right? So this bit here is greater than or equal to 1 minus 1 over 2 squared, right? Because the k value here is now 2. And so that means the whole thing is less than or equal to 1 minus. Okay, and then I got to finish this calculation. This is then 1 minus 1/4 or 3/4. So 1 minus 3/4 for the whole thing. So in the end, we get that the probability that x minus 8, right? How far are we away from the mean? Is it bigger than 6? Must be less than or equal to 1/4. Okay, I know there's like 2 negatives going on here, right? The first statement here was I was just focused right here, right? The probability of being inside that range is lower bounded by 1 minus 1 over 2 squared, which is 3/4, right? But then we take, then we go to the tails and we have to do 1 minus that. And because this was a lower bound for the center, it becomes an upper bound for the edges, right? You can actually do one more extension of this, which is to say, I'm going to have to draw a different picture, but same thing. So let's just do another example. Now we say sigma x is still 8. Not sigma x, mu x. Okay, mean is 8. Variance is still 9, so that means our standard deviation is 3. And it's an unknown but symmetric. All right, so that's something we always know, that it's equally likely to be on the two sides, but we don't really know the shape of it. If that's the case, right, well then my picture isn't valid anymore. Then maybe we do have, if this is 8 and this is 4 and this is 12, maybe there is a peak here, but that would mean that there would have to be a peak there. Anything on one side of 8 has to be the same on the other side of 8, and still trying to keep a standard deviation of about 3, which again, I've kind of stretched it out here, right? And then maybe we could ask a question that is like, what's the probability that x, and at least give me a bound for it. What's the probability x is greater than, let's go 3 standard deviations. So 3 standard deviations is, and by the way, k doesn't have to be an integer. We just often use it as an integer. 3 standard deviations is 9. So what's the probability that x is greater than 17? So there's 16, so 17 is right next to that. Out here is 20. We'll go purple this time. All right, so what can we make a statement about being way out here in this tail? And Yeah, we can do that by going in the other direction. Okay, so 17 is, by observation, is 3 standard deviations. So this is the mean plus 3 standard deviations. So because of the symmetry, I can come over to here and say, well, this is equal to a half of the probability, because of the, symmetric about 8, half of the probability that x is outside of 17 in either direction. So actually, let's do this a different way. Let's first say that this is, it's 1 minus, we're still using that, referring back to the center, 1 minus the probability that x is between 17, that's 3 standard deviations to the right, and 3 standard deviations to the left is minus 1. Okay? Sigma minus, or mu minus 3 sigma, mu plus 3 sigma. Okay? And it's 1 minus that, but not the whole thing. It's a half of that, right? We only want 1/2 of that bit, right? We only want one of the tails. Okay? Because that is everything, right? Where this is minus 1 and this is 17. Okay, so let's see. This is now going to be a upper bound. We're going to have this same inequality here. This bit in the center, I will just again take this. This is now lower bounded by 1 minus 1 over 3 squared, or 1 minus 1/9, so that means it's 8/9. And because it's 1 minus a lower bound, it becomes an upper bound. So the ending answer is that the probability that x is bigger than 17 is now going to be less than or equal to 1 minus 8/9 and only half of it. So that is 1/9 times 1/2, which equals 1/18. Okay, so whenever you go to the tails, it is a upper bound. So the probability is at most 1/18. It can't be any bigger. When you ask a question about the center, it's a lower bound. Okay, that's it. Again, I might come back and walk through the proof of this, but I'll consider that optional. Okay, so now to end this off, I just wanted to show the proof of Chebyshev's theorem. And again, I just pulled up my notes already written out here. So just, take it, just sit back and watch, right? And kind of allow yourself to justify why that theorem is true, right? And so I just drew just a randomly shaped distribution, any, sort of nuances I felt like drawing it when it was there, right? And again, I didn't put any vertical values here because that's it's just whatever those would be would just be to make sure that the area under the curve was 1. And because I was so arbitrary when I drew it, I didn't want to put those values in. Anyways, right? So now I say, like, consider the region outside the interval of interest. What I mean is k standard deviations away from the mean. Remember, we're confident in what the mean is, right? And then it has some unknown shape to the distribution. And then we're confident in the standard deviation so that we know that we've gone k standard deviations away. And that's what, our question is about. What's the probability I'm outside this region or inside this region away from the mean? And so that's what I have drawn here, right? So we've gone k standard deviations to the left, k standard deviations to the right. And so that means that, anywhere in this region, I call it A, is the value of x where x is less than mu minus k sigma, right? Over here, this is the region defined, I call it C, is x is greater than mu plus k sigma, right? And then in between, B is actually what the Chebyshev's theorem is in the end. It's going to be the probability in between those two things, right? So I just rearrange this region over here by subtracting mu, rearrange this one over here by subtracting mu, noticing that in this region, x minus mu is positive, and in this region, x minus mu is negative, but then we pull the negative over to the other side. When we do that, we have to flip the inequality, right? So this is also now positive, right? This is a positive number greater than k sigma. This is a positive number greater than the k sigma, right? So no matter how we write these two things, this region is defined to be x minus mu absolute value is greater than k sigma. That's going to work for both of these regions. In fact, it's a way to describe everything that's out. And in fact, this is kind of like the example we did, right? This says that start at mu and your value is, what's the difference from mu in either direction? It's bigger than k sigma. So I've gone further than k standard deviations away from the mean. That well defines everything I've shaded up here. It's regions A and C, right? Okay, great. So then we just square both sides. If this is true, then the region is also defined, x minus mu quantity squared is also greater than or equal to k squared sigma squared, okay? I want to then just focus on this sigma squared, and calculate it a bit more, okay? So now sigma squared, pull up our definition for the variance, okay? That's what the variance is. And this is an unknown thing, fx. So we never are going to have a shot at calculating this, right? We don't know f of x, right? But let's see if we can do something with this, right? We'll split into those regions A, B, and C. Here is that A region, right? Here is that B region, and all I'm just focusing on the bounds. From x values negative infinity up to that threshold of being k standard deviations to the left of mu. The C region is where we have k standard deviations to the right of the mean going to infinity, and that B region is everywhere in between. I say A is greater than positive, A is positive, B is positive, and C is positive, right? These are all positive things because all we're doing is accumulating a squared quantity, which is positive. F, probability distribution values, those are positive. Those are probability densities, those are always positive. So all three of these terms have to be positive, right? It's important that they're all positive so that we can have that inequality. Okay, so we can say that the variance is A plus B plus C, or we can say it's bigger than A plus C, right? Because all we're doing is canceling out what B is there, right? Okay. We then, in these regions, are free to replace x minus mu squared with k squared sigma squared. This is only valid in this A and C regions for these two terms. We've thrown out the B term by saying this is greater than or equal to, right? The variance is greater than or equal to this. Thrown out the B region. We're only limiting ourselves to the A and C region. Well, in the A and C region, this x minus mu squared is bigger than or equal to k squared sigma squared. So it's another way we've made this smaller, right? Okay. Because in those regions, x minus mu squared is lower bounded by k squared sigma squared. All right. We can do that. I mean, that's really helpful because then we can pull these out of the integrals. All right. We pull this out of the integral and we're left with this integral of f of x plus this integral of f of x. Okay. Well, this is just the probability that x is between, well, sorry, so this is the probability of, that x is either outside of, to the left of k standard deviations or to the right of k standard deviations, right? So in regions A and C, right? That's how you would calculate the probability. So another way to say that, this right here is 1 minus the probability of being within k standard deviations from the mean. Okay, so we then replace this with that. I rearrange this term just by dividing by that positive quantity of sigma squared. We just get 1 over k squared. Do some more rearranging, and we have the final form of Chebyshev's, right? Probability that x is between k standard deviations to the left of the mean, k standard deviations to the right of the mean, is 1 minus 1 over k squared. All right, so it's kind of weird, right? All right, and so we needed that expected value operator to define what the mean was there, and that's what we have. Oops, so jumping around here. All right, and breaking it up into these three regions, plugging in what the variance was. That's why it belongs in this chapter, but it also feels like it doesn't really belong in the chapter, but it's really powerful, right? So that's where we'll leave it, okay? A lot of weird things we did here, but trust me, anytime we left off a quantity or replaced something, we were being more conservative, right? So like we threw this entire term away and just put a greater than or equal to. Well, we lost a big chunk of our distribution, maybe perhaps in that, right? Maybe it's not a big chunk, right? This is like the deviations. Well, by definition, we're not that far away from the mean compared to these two terms, right? But maybe the probabilities aren't that big out here, right? So who knows how much we threw away? We just throw it away, We say it's greater than or equal to, right? We make another substitution. We replace x minus mu squared with k squared omega, or k squared sigma squared, and that's because we're out in these outer regions where we know that's definitely true. But again, we're being more conservative. So when you apply Chebyshev's, it's really just a bound, and the actual probabilities could be more extreme than that, but you got to be careful, right? In the center region, it's a lower bound. In the tails, it's an upper bound.